So like you have that, and then like you now created a vector function.
Vector field.
Vector field.
Okay.
And then if it turns out to be conservative, is that possible?
Yeah.
Oh.
Yeah. I mean, this is a perfect example. Let's say we did something and we've got this vector field. Let's show it's conservative, right? Let's show that it's the gradient of some scalar function. Now, it doesn't have to be. It could be, but it doesn't have to be. So what I need to do is basically go backwards and get back to that original function, right? Okay, so pay attention, because this is kind of easy to do when your vector field has two components. It's a little harder when it has three, right? So here's what I know. I want to show, right? I want to show there exists f, right, some scalar function, such that the partial of f with respect to x equals what? Let me write it this way. So we have the actual definition. The gradient of f is equal to our field, right? That's what it means for this to be conservative. It means that there's some scalar function that I should be able to find that when I take the gradient of that scalar function, I should get that field right there, okay? But this just means what? That means the gradient by definition is the partial of f with respect to x, partial of f with respect to y, right? That's what this left side means. That must be equal to the field that I just handed you, which is this, right? That those have to be the same. We will. Right? So I need to show that I need to find this f that keeps this equal, right? So let me start with the first thing. For two vectors to be the same, the first components have to be the same, right? Right. So my first thing is this. We must have that the partial of f with respect to x is 2xy, right? We have to have that. Agreed? When I differentiate my little f function, which I don't know what it is, but when I differentiate it with respect to x, I better get 2xy. That'll give me that first component, right? And we're trying to get f now, so what I want to do is integrate and go backwards to try and get f, right? This is a derivative with respect to x. So if I integrate this side, I get back to f. So I'm going to now do the integral of that with respect to x, and what I do there, I do on the other side as well. What does the left side become? Left side. The antiderivative with respect to x of the partial of f with respect to x undoes each other. You just get little f. Just little f, right? Little f. And then that must equal the antiderivative of this with respect to x, so you treat y like a constant. That should just be x squared y, shouldn't it? Okay, so this is where we have to be careful. It's x squared y, right? Plus normally c, right? But here's the thing, think about this carefully. All I know is that when I take the derivative of this with respect to x, I get that, right? That couldn't, do you agree that this could have constants, or it could have y's in it? Because when I differentiate it with respect to x, these y's would go away, wouldn't they? I just can't have x's here. I can have something here, it just can't have x's. It can have constants and it can have y's, but it can't have x's. So I can't say plus c. Instead, I'm going to say plus, I don't know, some function of y. We'll call it h of y. It's some function of y that I don't know what it is. Now that h of y might turn out to be a constant, but it could also have y's. I don't know yet. Yeah? Okay, now, this is how much I know about little f so far, right? This is how much I know, and it's not a lot, right? I mean, it's some, but it's not a lot. I'm off by a whole function of y. So now what I do is I use the other piece of information, right? Say, but these two have to be equal. right? Those two have to be the same, right? This has to be equal to that. But the partial f with respect to y must be equal to x squared minus 3y squared. We agree? And this is what my f is so far, right? F so far is this for us. So what I'm going to do is I'm going to take the derivative of this with respect to y and make it equal this. So what's the derivative of this with respect to y? Let's see. X squared. So this is the left side. X squared plus, what's the derivative of that with respect to y? H prime y? Something like that? I'm going to write it this way. H subscript y. It's a derivative of that with respect to y. I don't know what it is. So what I'm doing is I'm taking the derivative of f with respect to y using that f. That becomes x squared plus, that's the derivative of that with respect to y, which is h sub y. And that equals, now you have to take this right here, you're not taking derivative, right? These had to be the same. And what does that tell you? You can solve for the derivative of h with respect to y. You can just eliminate x squared on both sides. And that means that the derivative of h with respect to y must be negative 3y squared, right? Yes?
When we do this, should it always come out and they should want to do some function of y with no x's?
But with no, this should never have x's in it. That's right, this should never have x's in it.
I mean, at the end, so once you put the f of y equal to, once you take the derivative of the partial derivative of f and say equals f of y, should you always get, once you solve for h of y, should you always get just...
Oh yeah, you should never have x's in this answer, because that would contradict that you said it was only y's to begin with, or constants.
So I'm a little confused again.
Okay.
How you ended up solving for h of y. So the first thing you did is you integrated with respect to partial x. Then the next thing you did was...
So when I got to this step right here, I said, okay, I've got an idea of what f is, right? I've got an idea of what f is, but I don't know what that is. And then I came back to the second condition. The second condition for these two to be equal is that that has to be equal to that, right? So I wrote that down. That's this.
Okay.
And then I said, well, wait a minute, hold on. If I'm saying that this is f then, right, and I don't exactly know what it is because I don't know what that is, I know that when I take the derivative of that with respect to y, I should get this. So I took the derivative of this with respect to y, and that's what's right here. Derivative of that with respect to y is x squared, and then derivative of that with respect to y. I could have written it this way, but I think hopefully by now in Cal 3 we understand that like putting a prime isn't that great because it doesn't tell you what the independent variable is, right? It leaves out what you're differentiating with respect to. So this is a slightly better notation because it keeps track of your independent variable. So, yeah? Okay, and then from there the x squareds cancel on both sides. And then I'm there, and what am I trying to figure out? I mean, what was the one thing I didn't know about f? I knew that, but I didn't know that, right? I didn't know what h of y was. And now I know what the derivative of h with respect to y is, right? So how do you think I'm going to get h from that? Integrate it with respect to y. So take this and integrate that with respect to y. Integrate with respect to y, and then integrate this side with respect to y. Oh my gosh, it's already 217. All right, so that would give me on the left side what? Just h, right? Just h, or h of y. You could write h or h of y. You don't want to do h of y? H of y is fine. Okay, equals, now the antiderivative of this would be negative y cubed plus, and now you have to have a plus c here, plus some constant. And how do you know that this is not a function of x? Well, because we said earlier, right, that this is only going to be y's and maybe some constants. So I can use any c. So I think we've got it, right? Now we know what f is exactly. Well, not exactly. We've got a form for f. So therefore we have this. Little f of xy is equal to this, x squared y. And then this turns into minus y cubed plus any constant I want. And that should match what it came from, right? We had this earlier. We had x squared y minus y cubed, right? And this one is x squared y minus y cubed plus any constant. So if I put like, plus 1 or plus 2, we're still going to get the same gradient vector field. So we have a family of answers, don't we?
Yep.
So that's the way you do, that's the way you show something's conservative. Now, it's harder when you have a vector field with 3 components, because then you have to show that 3 things are true. And when you do your first integration, it's a little more, we'll see, we're going to do it. And then later, there's a simple check. There's a simple way to check if something's conservative. Yeah?
Is there, for something like this, would there be a reasonable way to find your C?
No, because it can be any C you want.
Okay.
Yeah, any C will work, because if you just replace that C with a number and then take its gradient, you're going to get that vector field.
Okay.
So you want it to be plus C. It's a family of answers.
Okay.
To be conservative, you just have to show that there's some scalar function it comes from. And we've shown that there's an infinite number of them.
Okay.
All right, 13.2. Okay, 13.2. Line integrals. Now, line integrals, it's a weird name for what it is. I have 20 minutes, so I can at least get this first part done. A line integral would make you think you're doing something with lines, right? And that's actually not exactly at all what we're doing. So it's a weird name for what it is. So take a look at this. You have a function of 2 variables, a scalar function, right? That's a scalar function, which is a surface. But what we're going to do is we're going to restrict that surface to, so we're going to define that surface, but only on a restricted domain. So I'm only going to take points in the domain that live on a curve, and I'm only going to plug those points into the surface. And if I do that, I get a curve that lives on that surface, right? Y'all see that? So we have a surface, but we're restricting the domain to a curve on the ground. Mapping just these points up into the surface creates a curve on the surface. And what we want to do is this. We want to imagine taking this. I'll make it bigger this way. We want to take that curve that we have there, and we want to imagine dropping a curtain from the curve down to the ground. Right? That's a curtain. That's not a solid, right? It's from that blue curve down to the red curve where it came from. Take that curtain, and we want to know its area. Right? Does that seem reasonable to be able to compute something like that? No? Okay, it's not reasonable. Let's call it a day. I agree. Okay, so look, this is not a stretch. This is not a stretch from what you've done before in Cal 2. See, in Cal 2, we were doing this already, but we were living on a flat sheet of paper like this, right? And what we were doing is we were taking a domain on the ground, which was an interval, and we were taking just those points, and we were mapping them up into a function, right? But it was only a function of one variable. So we had the curve up here, and then we were dropping a curtain straight down, and it would hit the x-axis, and then we were finding the area of that, right? And so when we did this, we used Riemann sums, and we said, hey, can we find a formula for one rectangle? And if we can, then we can use the integral to add them all up, right? So when we did this formula, that rectangle, it had as its height basically the value of the function. And then what was the width? How wide was this? Dx, right? When we did the limit, I mean, initially it's delta x, but then when you do the integral and the limit, this becomes dx. And so the area of that one little piece is the height of the rectangle times the width, right? That's the area of one rectangle, and then we use the integral from a to b to add them all up, right? That's the rebound sums. That's the whole idea of Cal 2 and the areas, right? Now what we're doing is we're just saying, hey, there's a slight change in plans here. We are no longer going to restrict ourselves to where the curve on the ground has to lie on the x-axis. It can lie anywhere. It can be any curve. And so our approach is identical to what it was in Cal 2 in the sense that what we're going to do is take an infinitesimal rectangle, right? So this is like an infinitesimal rectangle that lives on that curtain. And we're going to try and find the area of one of them, and then we're going to add them up with an integral, right? So can we figure out the area of that rectangle? So how high do you think it is? How tall do you think that rectangle is? F of xy. Remember, this is a surface, right? So you have to give me not only the x-coordinate, but the y-coordinate to give me some point in there. Then I take that, plug it in there, right? So this will be f of xy. And now the important part. How wide is it? What is that? It's a hypotenuse of something, isn't it? It's a hypotenuse. Wait, this looks familiar. This looks familiar. 10.3. The arc length of a vector function in two-dimensional space. If you give me a curve on a flat sheet of paper, I can calculate the length of the arc. And we use this formula right here. You've seen this. I know you have because I showed you. Where the hell? Where's my? Where's?
Down right there, right by the desk on the side.
Oh, there it is. Yes, this. I like this one. Thank you. All right. So we did this back chapter 10, section 8. This was eons ago. It said we need to pay attention to this. This is suppose we have a vector function that draws a curve. And we want to know the length of the curve from A to B. Then we would find the magnitude of the derivative of the vector function. Look kind of familiar? Later on, we talk more about it, and yeah, I mean, we basically are using this magnitude right here. This, I don't know why this cut off, but this square root should go all the way across there. I apologize, it's not there. So this was the formula we were using to find the length of the curve. So when we go and look at this picture, right, and I'm trying to find this length right here is this little infinitesimal arc length. It's an arc length, but it's infinitesimal. So this is going to be not dx, not dy. What should we call it? Like d something that has to do with arc length. Well, arc length, we use s for arc length. So we call this d little s. D little s, not to be confused with d capital S, which is coming later on in this chapter, where the capital S is a surface. And this is where I'm saying things are going to start to get mixed up because little subscript, big, little s, big S mean different things.
We're going to be finding the volume of a drop down into fourth dimensional space.
We could. I mean, that's the next dimension up, right? Right now we have a function of 2 variables. We're dropping a curtain, but what stops us from taking a function of 3 variables and dropping some fourth dimensional curtain down, right? That's what line integrals are, all right? So, all right, you got the idea geometrically? We've got that, and then we just need to add them all up. Now, this right here, that's basically the f of xy. And then this right here is the arc length. That's the ds. That's the arc length formula, right? It's the square root of the derivative of the x squared plus the derivative of the y squared. That's your r prime magnitude right there. Yes?
Where do we get our a and b for this?
Okay, so that's the next thing I need to talk about because this notation is slightly different than this notation, right? So the curve on the ground, right? The curve on the ground, C, that curve on the ground, you have to be able to draw it. And you need to be able to draw it with parametric equations. So then you have to go back to chapter 10 again when we talked about parametric curves and how you can take a vector function and you can write it in vector form or parametric form or symmetric form. Remember all this? And no, it's chapter 10, it's a long time ago. So this x of t, y of t are parametric representations of the curve on the ground, and the a and the b are the restrictions on the t that draws the curve on the ground. So all in all, what we need to do is be able to draw the curve on the ground with the parametric equations. And once we do that, we'll be able to get our limits of integration. Then we're going to take our scalar function, we're going to plug in the two coordinate functions for x and y, then multiply by the square root of all that, and then integrate that with respect to t and be done. Let's do an example. I think it's the best way to understand this. By the way, in red, because this is important, this is called the line integral with respect to arc length. The line integral with respect to arc length. Let's do the actual example that I showed you just a second ago. We're going to actually compute it. I have 10 minutes. I should be able to do this. So I see a lot of you are tired Easter weekend, Monday. I get it. I get it. I get it. Hopefully you come back rested. There's a lot of like glazed eyes. Chapter 13 is either going to make you or break you in this class. I know it's getting to the end of the semester. Everyone's exhausted, but I've warned you about this chapter since the beginning. This is the hardest part of Cal 3, is that we are now going to sprint to the finish line. And so please pay attention, okay, because I've been doing this long enough that I know that like this is where students disconnect, right? Because the 13 can overwhelm them. You're tired, you're taking other classes, right? So grind it out. So look at just the notation itself. We have to look at this thinking about you're at a final, right? You're taking the final exam, knowing what you have to do here. I'm doing a single integral, right? It's not a double integral. This is a single integral over some curve C, all right? So I need from that to understand that this is a line integral. And it's a line integral with respect to arc length because ds. Now, I'm also given that C is the upper half of the unit circle. So I'm going to go draw the curve C on the ground. This is my domain, upper half of the unit circle. That's my curve C right there. And so what I want to do is I want to move along this curve, right? I want to move along this curve, plug all those points up into the surface, and find the area of the curtain coming down. So I need to find a parametric representation of that curve, a parametric representation. So C, let me give you some parametric formulas. Here's the function. I'm going to give you the function for x and the function for y. So can somebody give me a way to draw that top half of the circle with parametric functions? Go ahead.
Cosine and sine x?
Cosine t, sine t. We'll use t instead of x. Cosine t, sine t. Now, this will draw me the unit circle. Why? Because the coefficient in front of the cosine and the sine is 1. If this circle had a radius of, let's say, 3, like if that was x squared plus y squared equals 9, then I would put a 3 here and a 3 here, right? Now, that will draw me the circle. I need some restrictions on this t because I only want the top half. So between 0 and pi, right? So we're going back to chapter 10, and we're saying, hey, remember when we were studying chapter 10 how to draw things with parametric functions? We are now utilizing that, right, just to draw the domain of our integral here. Okay, I've got that. Let's see. What else do I need? Let me bring the formula up here so you can see it right there. So if I want to do this, I'm now going to convert this to an integral from a to b. A to b are these two limits on these two restrictions on t, right? So my integral is going to go from 0 to pi. And now what I'm doing is I'm taking f and I'm evaluating it at the two parametric functions. So the original problem was what? 2 plus x squared, but x is what? Cosine. So it's going to be cosine squared t times sine t. Okay, that's the first part. And be careful, everyone. We're not doing a conversion into polar coordinates. We're not doing any of that, so don't be thinking we have to put a t in there. This is not a conversion to any coordinate system. We are just getting parametric representations of the curve. That's it. All right, what am I missing? ds, right? ds is the square root of the derivatives of those things squared. So maybe I should go get that information over here on the side. What's the derivative of x with respect to t? Negative sine t. And then derivative of y with respect to t? Cosine t. All right, so there are the two derivatives of these respectively. And so I need to multiply this by the square root of, oh yeah, that's going to be nice, isn't it? When I square those, negative sine t squared plus cosine t squared dt. It's the first example, right? Derivative of x with respect to t, that's that up there, squared plus derivative of y with respect to t, cosine. And then that inside the root is going to become a 1, right? Square root of 1 is 1. Any questions? No questions? So the new integral is integral from 0 to pi of 2 plus cosine squared t sine t dt. All of this, right, turned into a 1. And that right there should be a pretty straightforward integral. Let's see how straightforward it is. Antiderivative of 2 with respect to t would be 2t. And this right here, separate integral, cosine squared t sine t, that's going to be just a basic u sub. U would be cosine. The derivative of that's negative sine. You're off by a constant. What do y'all think? Negative 1/3 cosine cubed t. Given enough time, do we think we could get to this?
Yeah.
Yeah, 3. Okay, now we need to evaluate that from 0 to pi. Plug in pi. Let's plug in pi. I'll do it up here. Let's plug in pi. Then we'll plug in 0. All right, when we plug in pi, I get 2 pi. Over here, cosine of pi is negative 1, and then cube negative 1, and then that negative, so plus 1/3?
No, yeah.
Yeah. It's a double negative because I'm cubing it. And then plug in 0. When I plug in 0, I get 0 minus, and then 1/3, right? Because cosine of 0 is 1. So minus 1/3, and those don't cancel, do they? So I get 2 pi plus 2/3. So if you were to take that top half of the circle, map it into the surface, drop a curtain down, the area of that curtain would be this. I have 4 minutes. What I think is interesting, all right, what I think is interesting is if you go back, can I erase? If you go back and you think about an integral from Cal 2, let's say we were trying to do this integral in Cal 2, right? That integral in Cal 2. We see what that looks like? It's that, right? What I could do now is say, all right, this is the function f of x, y equals x squared. Okay, so it's this same shape, but now it's in 3-dimensional space as opposed to on a flat sheet of paper. And my curve, so it looks more like this. X, it's like, let's see, x squared, y. It actually, it doesn't really, it's going to go like this, like that. It's kind of like this shape. I don't know if you'll see that. It's like a piece of paper that's folded, right? Going down the y-axis. Y is a free variable here. And what I'm doing is I'm only going to integrate it over a curve down the x-axis. So my curve, what would my c be? What would my x of t be if I just want to move down? If I just want to move down the x-axis and go to 1, I could just make it what? T, right? T, and then what would my y of t be? I don't want to be anywhere on the y-axis, right? I just want 0. And then my t would go from 0 to 1. Just look at that for a second, see if that makes sense. I'm going to be able to move down. This is my x-axis. Okay, my x-axis goes this way. This is now the z, not the y. X, and then I don't want to come this way at all. So this should do it, right? I just go from 0 to 1. That should move me down the x-axis from 0 to 1. And the y-axis, we're just going to stay on the y. Following or no? Yeah, kind of. If you do it this way, then your line integral, right? Your line integral would be the integral from 0 to 1, and then it would be this evaluated where? Replace the x with t, so t squared times, now you need the square root of, what's the derivative of this with respect to t? 1. Derivative of that with respect to t? 0. So wouldn't that just be 1 squared plus 0 squared dt? And isn't that the exact same integral? It's just t squared instead of x squared. So what I'm saying is every integral you did in Cal 2 could be looked at as a line integral here, where all you're doing is making this change. That's the change. That's the change. And this would be from a to b, right? So every line integral, or every Cal 2 integral was a line integral here. So what we've done here is we've abstracted the idea out now where you're differentiating here. This right here used to just be dx for us, but now it's not. It's this arc length. All right, we are out of time. So what are you going to do? Try and do homework up through 13.1. 13.1 homework's not that bad. Have a good day. Eat your Wheaties and come back on Wednesday. We keep grinding away. This section's long. It's long.
Okay, Professor, when's our next mini exam?
Oh, the mini exam, I'll get it out to you. I didn't have it ready to go today, so I will get that out.